Hey, so you've heard the word blockchain thrown around a ton, right? It's almost always tied to things like Bitcoin and crypto, but what is it really? Well, today we're going to pull back the curtain. We're going to deconstruct the chain, get past all the buzzwords, and really understand the core tech that's changing, well, pretty much everything.
So here's our game plan. We're going to start with the absolute basics. What problem was this even designed to solve? Then we'll get into the cryptographic magic trick that makes it all so secure. After that, we'll look at the massive global puzzle that decides who gets to add new links to the chain. From there, you'll see this is not a one-size-fits-all deal. We'll check out some mind-blowing real-world uses, and finally, we'll look at the one thing that could be its ultimate downfall.
All right, let's dive right into Section 1. What even is a blockchain? Before we get into all the nuts and bolts, we really have to start with the why. I mean, what problem was so big that it needed this wild new invention? It all boils down to one simple but incredibly tough challenge. How do you create trust in a digital world?
I mean, really think about it for a second. Any file on your computer, a Word doc, a photo, a spreadsheet, can be copied, pasted, and changed a million times over, right? So how on earth do you create a digital record, like a ledger, that everyone can agree is the real one and that no one can secretly mess with? That is the billion-dollar question. And here's the answer: a blockchain. The easiest way to think about it is like a very special shared digital notebook. Now, there are two keywords you absolutely have to remember here: distributed and immutable. Distributed means it's not in one place. It's copied and spread out across thousands of computers. And immutable means that once something is written on a page, it can never, ever be changed or erased. And that simple, brilliant combo means we don't need a middleman like a bank to vouch for everything anymore. Yeah, this visual really says it all. For pretty much all of history, our systems have been centralized. You have one main server, one point of control, and of course, one single point of failure. A blockchain is completely different. It's decentralized. There's no hub. There's no central command. Every single person on the network has a full copy of the ledger. So it's a system that's literally owned by its users, not some big corporation.
Okay, so let's zoom in and look at just one page in this digital notebook. We call it a block. And each one holds three really important things. First, the data itself. This could be anything, like financial transactions or medical records. Second, a unique digital fingerprint for that data, which we call a hash. And third, and this is the absolute key to the whole thing, it holds the fingerprint of the block that came right before it. That previous hash is what literally forges the links in the chain, locking them all together in order.
So that brings us to Section 2. We're going to talk about that digital fingerprint I just mentioned. This hash is the secret sauce. It's the cryptographic magic that makes this whole system basically tamper-proof.
So what is hashing, really? Well, think of it like a super advanced data blender. You can throw anything you want into it, one word, a whole movie, the entire Library of Congress, and it spits out a unique string of letters and numbers. But here's the trick. It's a one-way street. You can never take that final code and work backward to figure out what the original data was. It's a digital dead end, and that is its most powerful feature.
You know, this is something a lot of people get mixed up, so let's just make it super clear. Encryption is a two-way street. You use a key to lock up some data, and then you or someone else can use a key to unlock it. It's all about keeping things secret. Hashing is totally different. It's a one-way trip. It's not for secrecy, it's for integrity. It's just there to prove that the data is authentic and hasn't been messed with, not even by a single comma.
And this shows you just how incredibly sensitive it is. Take a look at this long string of characters. What do you think that's the hash of? Well, believe it or not, that is the SHA-256 hash for absolutely nothing, an empty string. If you were to just add a single dot, the entire hash would completely change into something totally different and unrecognizable. This is called the avalanche effect, and it's the bedrock of the chain's security.
Okay, let's put it all together. Imagine some hacker tries to go back and secretly change some data in an old block. Well, that tiny change, no matter how small, instantly creates a brand new hash for that block. But the next block in the chain is already storing the old hash. See the problem? The link is broken. The chain is visibly shattered, and the entire network of thousands of computers would instantly know something was wrong and reject the fraudulent version. It basically polices itself.
Okay, so the chain is secure. We get that. But in a system with no boss, no one in charge, who actually gets to add the next page to the notebook? How does everyone agree on what's next? Well, that brings us to Section 3 and the whole idea of mining. The most famous way to do this is something called proof of work. You can just think of it as a giant worldwide lottery that never stops.
Computers all over the planet, which we call miners, are all racing at the same time to solve a really hard math puzzle. The very first one to find the solution gets the right to add the next block to the chain, and as a thank you, they get a reward. This intense computational work is what makes attacking the network so unbelievably difficult and expensive.
And what's really cool is, this idea wasn't even invented for Bitcoin. It actually started way back in 1997 with something called Hashcash. It was designed to stop email spam by forcing spammers' computers to do a tiny bit of proof of work for every email they sent, making it too costly to send millions. The idea was later adapted for digital money, and then, of course, Bitcoin made it famous as a security backbone for a truly global, decentralized network.
So, what is this puzzle that miners are solving? Well, they're basically just looking for a single lucky number. It's called a nonce, which is just a fancy way of saying number used only once. And the process is just pure brute force guesswork. They take all the data for the new block, they guess a nonce, and they hash it all together. If the final hash doesn't meet the network's very specific target, like say starting with 19 zeros, they just change the nonce by 1 and try again, and again, and again. Literally billions and trillions of times every single second.
And just to give you an idea of the scale we're talking about, this number you're looking at was the actual winning nonce for a recent Bitcoin block. So out of more than 4 billion possible numbers for just this one part of the puzzle, and with trillions of guesses happening every second all over the world, one computer at one exact moment guessed this specific number to produce the winning hash. That was the one winning lottery ticket. It's pretty mind-boggling.
Now, here's something that's really important to understand. Blockchain isn't just one single technology. It's more like a flexible recipe, and different projects customize the rules of the game for their own specific reasons.
For instance, not all blockchains use the same puzzle. Bitcoin's puzzle, called SHA-256, is all about raw, blistering calculation speed. Well, that led to the creation of these hyper-specialized computer chips called ASICs that do nothing but mine Bitcoin, which turn mining into a huge industrial business. So in response, other networks like Litecoin and early Ethereum chose puzzles that were memory hard. These puzzles need a lot of RAM, computer memory, not just pure speed. And that was a deliberate choice to try and level the playing field so that regular people with powerful gaming computers could still compete, which helps fight against that kind of centralization.
And there's another huge difference: public versus private blockchains. The permissionless ones, like Bitcoin, are like a public park. Anyone in the world can join in, see the ledger, and participate. They're all about radical transparency. Then you have permissioned or private blockchains. These are more like a private country club. You need an invitation to get in, and some central organization decides who can do what. Big corporations often use these because they're way more efficient and give them the control and privacy they need.
Okay, now this is where it gets really cool in my opinion. We're going to move past all the talk about cryptocurrency and look at how this exact same technology is being used right now to solve real, everyday problems. And honestly, the applications are just exploding everywhere. Let's talk about food safety. Companies like IBM and Walmart are using blockchain to track produce. So if there's an E. coli outbreak, they can trace a specific head of lettuce from the store shelf all the way back to the exact farm it came from in seconds, not weeks. That saves lives. Or how about education? MIT is now issuing digital diplomas on the blockchain, so employers can instantly verify they're real, making them completely impossible to fake. From voting systems to real estate, the core idea is always the same: create a single shared source of truth that everyone involved can trust without question.
So, we've spent all this time talking about how secure and unbreakable the chain is, but we have to end this by looking way out on the horizon, at the one massive long-term threat that could, potentially, bring this entire digital fortress crumbling down: quantum computing.
Okay, so here's the deal. Once they get powerful enough, quantum computers could attack the blockchain in two major ways. The first is with something called Shor's algorithm, and it could threaten the digital signatures that prove you own your coins. It's like having a master key that can unlock any digital safe. The second threat is Grover's algorithm. It could make the mining process so incredibly fast that a single person or group could overpower the entire network, letting them rewrite history. That's the dreaded 51% attack.
But you know what? The race is already on. Brilliant people all over the world are working right now to develop new kinds of quantum-resistant cryptography that's designed to survive this future storm. And that leaves us with a huge, fascinating question. As this new era of computation finally arrives, will our digital fortresses be able to evolve fast enough to withstand it? It's something to think about. Thanks for tuning in.